Okay, we're going to talk about the second part here. And again, we talked previously about a thermochemical equation, a chemical equation that includes heat values in it somewhere, some way, that lets us know whether something is exothermic or endothermic. Equations letting us know it's a balanced equation. Now, there's some rules for when we analyze chemical equations, and these are going to come up later on when we do some manipulation of equations in an idea called Hess's law. And now that's coming here in a couple days. So let's talk about some of these rules and talk about how um, they apply to thermochemical equations. So the first rule is this: the magnitude of delta H is directly proportional to the amount of reactant being consumed in a reaction. So let's say we take a look at a mole of CH4 burning. So we have CH4 burning in oxygen to give us CO2 plus H2O. I'm going to balance this guy really quickly here. And so one carbon, two hydrogens, we have two. And so we're balanced. So we really do. We have a mole of CH4, 2 moles of O2, 1 mole of carbon dioxide, 2 moles of water made. Now, when a mole of CH4 burns, we get a delta H value is equal to negative 890 kilojoules per mole. And that lets us know how much heat is being given off. Kilojoules, as I mentioned before, and if I didn't, this is just going to be our unit of heat value of kilojoules. Now, when we double the amount, let's say we go up to 2 moles of CH4, which is going to require 4 moles, and it's going to produce 2 moles here and 4 moles here. Essentially what we're going to do is that means we double the amount of heat that's being given off 2 times, and that's the way the rule works. Okay. Now, the second part of the rule is going to be delta H for the reverse reaction just changes the sign of delta H. So if we take our first equation and reverse it, let's say we go with 1 carbon dioxide plus 2 waters is reacting to form 2 oxygens plus 1 methane molecule. We've essentially taken this reaction here and we reversed it down here. So what we're going to do is our delta H value is going to become positive. It's going to flip around. Positive 890 kilojoules per mole. So the only difference between those two is that value. This is going to be an endothermic reaction, and this one up here is going to be an exothermic reaction. Okay, the next thing we could talk about is delta H for the reaction is going to depend on the state of the reactants in the products. So if we're going to combust the same reactions we talked about before, if we're going to combust a mole of methane and it turns out and it gives us liquid water, it's going to be 890 kilojoules that are going to be given off. But if we are going to combust the same mole of methane and it's going to give us a gaseous form of water, we're only going to get 802 kilojoules. Now, the reasoning behind this is, and really what this is all about, is we need to make sure we watch our states when we do calculations. We'll do this later. Is if we were to take some liquid water and we want to just take a liquid water and convert it to gaseous water, well, that's a liquid to a gas, which is, we can call it evaporation or we can call it vaporization. Really depend on where it's at. It's going to take some heat. This is because this is an endothermic process, and the amount of heat that it takes is 88 kilojoules per mole. And so, with that said, that's why you see a difference between 890 for the water and 802 for the gas, because it does take it's going to take some amount of energy to convert that liquid water to gas water. Hopefully that makes sense. Now, the last thing we're going to talk about for tonight's lecture is the calculation of the heat released. Now, we talked about it before with respect to this same balanced equation that we're working off of, this methane reacting with 2 oxygens to form 1 carbon dioxide plus 2 waters here. If we were to look at this, we said before 1 mole of methane completely combusting is going to give off 890 kilojoules per mole of heat. But let's say a problem gives us a grams measurement of methane. So 4.50 grams of methane is given to us. And so what we're going to do is we are going to just do a quick little conversion. We're trying to get to a value in kilojoules per mole over here because we want to know how much heat is being given off. And so really what we're going to do is, first thing we're going to do is we're going to convert methane from grams into moles. Real easy conversion, 1 mole of methane over 16 grams of methane, the molar mass of methane. And that just gives us a conversion. Then we know in every 1 mole of methane, it's going to give off 890 kilojoules of heat. And so now we've just set our problem up. And so grams is going to cancel grams, moles, moles, just like that. And so it's going to be 4.5 multiplied by negative 890 divided by 16. And so that's going to give us our answer. And the answer that I came up with was negative 250. We'll call it kilojoules, just like that. And that's the amount of heat that's going to be given off. Obviously, if we had over here 16 grams of methane, well, that'd be a mole of methane, and that would give us negative 890 because the 16s would cancel. We had less than a mole, essentially a fourth of a mole, based on that. So our answer is about a fourth of 890, roughly, not really exactly there because we had the 0.5. But anyway, that's tonight's homework, and that's all we got. We have 2 parts to this video. Have a nice evening.